remember, 6.8 million stars. And some of them are, and there's two different kind of flavors. One are wider doubles that are more conducive for smaller telescopes or easier observations, and the rest are kind of go all the way down to kind of like mag 18 secondaries and very close doubles. So you can have a lot of fun with that depending on the tools you have available for observation. So I thought I would show you the program, and we can talk about the different things you can do with it. It's really super simple. So that should take only a little bit of time. And let me see if I can share my screen so I can run it on my machine. That looks promising, main screen. Okay, do you see my screen?
Yeah. Mm-hmm.
Okay, good. Now, where is it? There it is. Okay, so now you should see, I just double clicked on this little shortcut. So now you should see GDS 1.0. Mm-hmm. Good. Okay, so it really is simple. Right now it's loading. You can see down here. I don't know if you can see my cursor or not. Sometimes
we can.
Good. So it's reading the catalogs. And there are two catalogs that it reads. It reads my two custom catalogs. One's called GDS something, and the other one is WDS, which is the Washington Double Star catalog.
Finished. 6 million Gaia doubles in there?
Yeah, it really has 6.8 million Gaia doubles.
Okay.
Okay.
And those are all stars whose parallax is similar and proper motion is similar and whatnot?
More or less. So I'll talk about that in a minute. That's an interesting question. So we don't know if they're gravitationally bound systems or not, but I've developed kind of a very crude estimate, if you like, for the probability or the possibility that they're gravitationally bound. I wouldn't take that with too much. I take it with a grain of salt, and I think it requires a lot more work, but at least it kind of heads you in the right direction, if you like. Okay, so it's been a few months since I've actually run this, so let's see if I can remember how to run my own program. So up at the top, there are selection filters. So you can specify a minimum and a maximum right ascension declination, of course. Comp 1 mag is the primary magnitude. I should have labeled it primary magnitude. Delta mag, which is the minimum and maximum delta magnitude between the two stars in Gaia G band. So Gaia G band is very broad band. Basically, it's the instrumentation bandwidth of the satellite. A minimum and maximum separation. Now, I discovered that the data, the Gaia data has really a minimum of about 0.5 arc seconds. So there are no double stars resolved with the Gaia telescope that are less than about a half an arc second. Okay, and that's just that's a problem. That's because their aperture has a finite size, and their techniques for separating stars have a certain signal to noise ratio requirement and so forth. Anyway, so they only can separate down to about excuse me. So, and in the documentation, which I probably should bring up, let me think. Right. me go find the documentation. There we go. So there's a little bit more information about this whole thing here. And can you see this?
Yes.
Good. So I'll read it to you. So there are two kind of flavors of double stars that I've searched for in the data. The first, which has the vast majority of the doubles, is where the primary is less than 15 mag, the secondary is less than 18 mag, and the separation is less than 5 arc seconds. So that's kind of a nice collection of double stars for interferometric techniques. Okay, it's bispectrum or regular. And then there's another group that's comprised of about 500,000 that are brighter, the primary less than 12 mag, secondary less than 17 mag, with a separation between 5 and 10 arc seconds. So they're kind of brighter and more separated, and that's a good group for maybe doing things like visual observation of double stars or CCD observations and so forth. So that's kind of important to know. Now back to, hey, don't do that.
And
So
are these stars also particularly in the second of those categories, I imagine some are in the WDS and some are not?
Many are in WDS, and I'll talk about that in a minute. So let's actually run this now. And I'll get into what the gravitationally bound index means in a sec. But let's just, I have some filters set up here. I'll just apply them. Okay, so this is every double star that has a declination between 27 and 28 that's in the Gaia catalog based on these selection, this set of parameters. Between an RA of 18 and 19 hours, and so forth, with other filters that are applied. You can pretty much ignore the first 3 columns because they're kind of internal numbers that I use. So these reference catalog entries, but these are my own sequence numbers for the catalog. They don't mean a lot. The RA and DEC mean a lot, of course. That's the coordinates J, 2015.5, I think. The position angle and the separation, the magnitude of the primary, the magnitude of the secondary, the differential mag, which is just the difference of these two, this gravitationally bound index, which I'll describe in a minute, Gaia flags, which may or may not be interesting to you, whether or not it's in the WDS catalog or not, whether I found it in the WDS catalog. A lot of the entries in WDS don't have perfectly accurate coordinates, so you got to be a little bit careful with this. This means that I found something close by, and you can go and check on it yourself to see whether you think it's the same double or not. In many cases, it's obvious. In some cases, it's not quite so obvious. This is B minus R. So it's the color index for the primary, and this is the color index of the secondary where there is one. Blue minus red, basically. So Gaia has this broadband spectral response, which is called G. It's kind of all of the light that comes into the telescope. And then there are dichroic filters that split that light into B and R pretty much down the middle, in a sense. So most of the light, if you summed B plus R, you'd see that it was most of the light that came into the telescope, which comprises G-band, but not all of it. So you got to go take a look if you want to know more about that, and you can see what the spectral response of those two other bands are.
So those don't correspond to like any SDSS filters or anything? It's just splitting it?
I think Rick might actually know more about it than me.
I think they're in the neighborhood, but they're just a more or less equal division of the whole broad spectrum from probably about, I don't know, 350 nanometers out to almost 1 micron.
Yeah.
Okay.
And you know, the B is the blue half, and the R is like everything from, I don't know, 600 out to 1 micron, more or less.
Wow. Okay.
So they're wider, I think, than any of the normal photometric bands.
Okay.
Now there are filter transformations to I think Sloan but they're only unidirectional. They're not bidirectional transformations. So it's kind of annoying. You can't take the Gaia B minus R and so forth and convert it into say Sloan spectral response.
What is the reason we would do it this way? What information do we get with such wide filters separated like that?
Well, you get a very nice color index, so you can estimate the spectral type of the star.
Okay, you can estimate it.
So, a G or a O or a or so forth.
Okay, so
if you remember well, maybe you're not familiar with it, but I think the original purpose of this satellite was not to focus on stars, but to try to get a three-dimensional picture of the entire universe, including who knows what, quasars and stuff that's so far away you can't, can't get accurate distances, but you can tell colors of way out there stuff. And that's another reason that they didn't focus on close resolution either. They wanted to cover a wide part of the sky, so the pixels are fairly big chunk of sky, on the order of a fraction of an arc second, not hundredths of an arc second.
Right.
So it is what it is. Stars are almost a fortunate byproduct.
Yeah, it's still amazing. Okay, thanks.
Yeah. Is there a way to, is there like a lookup table where there's an estimate of the spectral type based on the B minus R index?
Your sound has faded out. It's kind of hard to hear you, Kelly.
Oh, I'm sorry. Can you hear me now?
Not very well.
Oh dear.
Yell.
Way in the background.
Oh my. I'm sorry.
A little better.
I will speak louder.
Good.
Is there a way to estimate the spectral type based on B minus R index, like a lookup table or something?
There's a beautiful graph that'll show you that's on the Gaia website. So if you go to, Rick, do you have the link for the website handy? I could find it if you need it. I'll send it in an email if you can't find it. But I
don't have it handy, but yeah, I'll look for that image. I think it's a nice fat HR diagram.
Oh, yeah, I've seen that.
Yeah.
It's kind of wide because it includes everything that's found so far, stuff that's near the main sequence and a little bit starting to change away from the main sequence or even approaching the main sequence. So it widens the magnitude range.
Cool.
There's a lot of beautiful information, data.
Yeah, it's
that's been boiled down. There are so many beautiful things that have come out of this that it's worth an hour or two just to go searching around on the web and looking for stuff. Okay, so anyway, back to the main topic. So here's a little example, a very limited range in declination in RA. If I widen the range, let's say I went from deck 0, which might be of interest, to deck, oh, I don't know, what, 50? And we hit apply, we'll get a nice big long list now of double stars that, now again, these are, so I'm sure that they are in the catalog, but because they're in the catalog and they're close by in the catalog doesn't mean you'd actually find them if you took an image. So you got to be a little bit careful with catalogs. Catalogs can have interesting problems. You can find the same star twice in 2 different locations that are closely separated. You know, it's all a bunch of software. So be a little bit careful. Although Jocelyn and Richard and Rick have all found these stars, these double stars, and I have too, doing speckle interferometry, taking images and doing speckle. So I think, and I haven't found a case where I didn't find the thing I was looking for. So I think, at least in a very, very small, limited example, the catalog works pretty well. This tool works pretty well. Okay, so here's a big, nice, big, long list of stuff that you could go looking for. You can sort this list. So interesting ways of sorting this list might be, well, the magnitude of the primary might be a really nice way. So if you hit that and you hit apply again, it will resort the list. Now the list is in order of ascending magnitude. So here we have a magnitude 8.4 primary star, and we go all the way down to what, you know, our limit was 8 to 12, so we go all the way down to 12 mag primary. So if you're looking for candidates to look for, that might be one interesting sorting technique. Another one might be the separation, of course, right? So let's sort by separation. And now it's an ascending separation, but we might want descending. So if we just hit this and hit apply again, now it's from the widest to the narrowest separation. And so you get the idea. You can sort by lots of other things that might be of interest. You can sort by B minus R of the primary. And so that would be a very red primary. And now you're kind of in the blue end of the primary. So get the idea. If you want it to be, if you always want to have what's called 3-band photometry, in other words, they were actually able to do the photometry in 3 bands for both stars. So you have, both stars have a color index. You can check that box and apply. And now we have, you see we have a color index for every star, or at least we should. There's a guy that doesn't. I don't know why he showed up.
So the 3-band photometry, that's the full, the whole sort of spectrum, and then the 2 halves. Is that correct?
Yeah, actually, I think they only, I actually haven't found a definitive answer to this, but I think they only did the photometry in 2 bands, B and R, and G is a reconstruction, is kind of a software reconstruction from the 2 bands. But I'm not totally sure, to tell you the truth.
Okay.
Okay, so, but it's called 3-band photometry by other people.
Okay.
And let's see, so if you don't like the decimal degrees, then you can click on this checkbox, and The normal kind of, I love decimal degrees for other reasons, but other people don't because software sometimes requires
Right.
this format. And if you want it to be a WDS member, check that box and hit apply. And now it only shows the stars that I also found or the doubles I found in the WDS catalog. So again, be careful with this because it's a little bit tricky because the coordinates in WDS are sometimes quite far off. So I could have found something in WDS catalog that really isn't the same double star. But I think in almost every case it is, but I have found a case or two where it wasn't. So be careful.
Is it useful in the bigger picture to let the like Brian Mason at the Naval Observatory sort of know, like in those couple cases, is it useful to say, hey, these coordinates are a little bit off, or does it not really matter at this point in the vast data?
I have no idea. I haven't contacted the folks at WDS to even ask them the question of whether this would be useful. I did send them this program. I sent a link to this program as a CC on one of Russ's emails, but I didn't hear back from him.
Okay.
I'm sure that they are well aware of the issues with some of the coordinates for some doubles, and I'm sure they're working on their own Gaia version of just like this. So they're very clever and smart people, and I'm sure they'll, be able to adjust the catalog accordingly once they. Okay, so you get the idea. It's really simple to use. There are some nice things down here. Let's select and see if I can remember how to use it. You can click on things. Suppose you're interested in those guys. You can click on those guys, and then you can, let's include the WDS data. So I'm clicking on that checkbox. Let's write all of the records, and then let's write a CSV file with that information in it. And it asks you for a file name, and I love the word test. GDS, so I might be able to find it sometime in the future. And right, it kind of disappeared. Where did it go? Let me find it in my folder. Oh yeah, it actually the default location is where the executable resides. So in fact, there it is. Let's see if we can. Oh yeah, so I want to actually open it in Word. Sorry, Excel. Let's open it in Excel. It should have appeared here. Recents. Okay, and here we have it. This is a big, long, kind of ugly Excel sheet, but it has the columns labeled, so you can you'll get the idea real quickly. So you have RA index, right, of the primary, RA index of the secondary, the PA that I calculated from Gaia, the separation I calculated from Gaia, the gravitationally bound index, which I haven't talked about yet, whether or not it has 3-band photometry, but I asked it to, so it should. The magnitude of the primary, the magnitude of the secondary, the so the bands are called BP and RP. I don't know why. The Gaia bands are BP and RP. So there's the BP magnitude of the primary and the secondary, R magnitude of the primary, secondary, and on. So the documentation, I think, contains a list of, let's see, yeah. So here is, without boring you to death, here's a list of those columns and what they mean.
So cool.
So you can pull out whatever information is interesting to you from this CSV file and further process it, looking for things to look at, things to observe.
Are the T effective and the luminosity, do those both come just from the B minus R, or is there another variable that plays into that?
That's a really great question. So the clever folks at Gaia have figured out how to estimate, these are only estimates, how to estimate the effective temperature of the surface of the star based on the parallax, so based on the distance to the star, the star's luminosity, and its spectral type. So, but to do that, you've got to assume that it's sitting on the main sequence, or maybe you assume it's a red giant. But if it's on an off-sequence star, this probably doesn't work. And again, you can go look for this information on the web and read about it. Read about how they do the estimate and so forth. It's quite interesting. So the luminosity has to be estimated by the apparent brightness and the distance is estimated by the parallax and so forth. So you get the idea. So the radius you have to estimate, you have to assume it's a main sequence star, or it's on, you can place it on the HR diagram. And that's a bit tricky.
You see all those values that have an exponent of 20. That's just the default for we don't have any idea.
You couldn't make an estimate for whatever reason. The SNR wasn't high enough or whatever. So anything that looks like a weird big number, well, that's just my number that says that there was no data available from the catalog. These are the radial velocities. You can see in many cases they couldn't estimate the radial velocity, which makes sense. Radial velocity require really good spectroscopy, and if the SNR is low, you can't do spectroscopy. Okay. You can see here I've included a WDS name. So that's the actual thing that I found in the WDS catalog that met my criteria for saying that it's a correspondence. And as I said, it's usually the case, but not in every case. Is it right?
Is your criteria based on RA and DEC within a certain error range?
The criteria is based on exactly the location of the primary star, and the location of the double in the WDS catalog, and it had to be within, I think, 10 arc seconds.
10 arc seconds, okay.
Or I may have had to change it to 30. I can't totally remember. Maybe documentation. But then I also applied a filter where if the brightness of the primary was very far different from the Gaia brightness, then I also rejected it.
Okay.
This is the familiar discovery code. So here's the WDS name, here's the discovery code, and the components. The usual WDS nomenclature that you're probably familiar with. Okay, then all of this stuff here is the WDS data that I extracted out of the catalog. The RA and DEC given by WDS, but I think it's transformed boy, you know, I can't remember exactly, but I think I transformed it to J 2015.5. In other words, the same.
Yeah.
Let's see if I actually put that in the notes. That's an important thing. Nope, so I didn't transform it. This comes right out of the
Okay.
WDS catalog. So I had to figure out what the WDS catalog actually meant in terms of coordinates, and it's not well documented. But it turns out that it's really J2000. So the observations are transformed back to J2000 for the WDS catalog.
Is
The
that
value is,
is
pardon me?
that true for all of that? Like the coordinates in the WDS catalog are transformed to J2000 even if the observations were made prior to that? They're sort of gone forward based on the proper motion or something?
That's what I discovered, yes. That J2000 coordinates, I hope I've got that right, but that's what I remember.
Okay.
Now, as you probably know, there's two things about coordinates that you have to know. One is the equinox, which is the J2000 thing, and one is the epoch, or epoch, as some people pronounce it. E-P-O-C-H, right? Epoch or epoch. The epoch is tells you about proper motion. So, and they don't have to be the same. For proper motion, you may have to allow the star to move. So you may see a coordinate where the coordinates are in J2000, but the epoch is, I don't know, some other year, some other time. So you got to be careful with that. And I won't bore you with the details of all of that stuff, but just to let you know that it does require some care for double stars because the stars are moving, and they can be moving at a fraction of an arc second per year in some cases. And so you can get yourself into serious trouble. You know, if you have a double star and the two stars are rotating around each other, as we know, we want to actually find that orbit by taking data, you know, many times in a decade or something. And so you may transform those coordinates back to J2000 to be convenient for other people, but you have to tell them the epoch of the measurement to know exactly the precise location of those stars in terms of proper motion. Okay. What else is in here? Right, this is all the information that came out of the WDS catalog, which you're probably familiar with. Number of observations, the magnitude that was recorded for the primary and secondary and so forth, and spectral types. Okay, so that's the CSV file, which can be quite useful if you're planning a campaign. You can further reduce this information as you need to actually set your telescope up to do automatic observations or whatever. That. I think I accidentally closed this. Okay. So I think the last topic is, what do I mean by the gravitationally bound index? So what I wanted to do was to really very roughly see if I could estimate the likelihood that the pair of stars were gravitationally bound or not. Because there's a lot of information in Gaia that could help with that. Obviously, the separation, they're close together, so that's a good thing. But we also have radial velocity, we have parallax, and so forth. So you can take things like and we have maybe even more important, we have the proper motion of the stars. So if they're moving, if they're kind of co-moving, I think it's going to be more likely that they're actually a gravitationally bound pair. And if they have the same, so that means that if they have the same proper motion and they have the same radial velocity or similar, that suggests that they have a higher likelihood of being gravitationally. That's basically what I've used here. So here's how it goes. I subtract the proper motion in RA, and I divide it by the sum of the standard deviations, the calculated standard deviations of the proper motion in RA. And this is statistically not correct. And I'm the first one to admit that a mathematician would have a fit. However, this is easy to do. And I'm not trying to make a final scientific determination that the pair is gravitationally bound. I'm only saying that this is a nice index so that you could go look further into the problem. Maybe you could take your own measurements, and if you had a spectrograph, you could actually spend more time dwelling on this object to get the spectra of the two, get a more accurate spectra of the two. You get the idea. You could actually use this information to go probe this further. So it's really important that you understand that this is only kind of just a rough guess. But we'll take a look and see what we have here in a minute. So to this statistically kind of incorrect estimate of the two stars having the same proper motion, I add to that this statistically incorrect estimate of the parallax. In other words, are they the same distance away to some reasonable, degree? So if they have the same proper motion, they have roughly the same parallax, and they have roughly the same radial velocity, and then I say that there is a higher likelihood that they are gravitationally bound. I thought about this for quite a long time, and I looked into the statistically correct methods, and I'm not sure that they're any more useful than this, to tell you the truth. This is a tough subject, but this could be a fun project to think about some more, and maybe to actually go take images and try to figure it out, or even do some work with high resolution spectrograph. Anyway, you get the idea. So let me run this again, and let's talk about what this means. So I actually shouldn't have closed that spreadsheet, and maybe we'll go back to it and see if I can find it again.
By the way, Dave, this is so awesome. Thank you for doing all this. I can't wait to get.
A real pleasure. I hope it's useful, and I had a lot of fun doing it. So let's take an example. There's like too much information here. So the lower this index is, the more likely it is to be gravitationally bound, because it's the difference in proper motion. It's the kind of the normalized difference in proper motion, the normalized difference in parallax, normalized difference in radial velocity. It's kind of summed together. So if it were to be zero, then they would have exactly the same proper motion, exactly the same radial velocity. You get the idea. So here's a case where it's pretty low. It's only 0.5, kind of normalized units. So let's go see why. So the measured separation is about 1.2 arc seconds. The magnitude of the primary and secondary are quite similar, interestingly. Let's scroll over here and see what I can.
Parallaxes are similar.
So let's see if the parallaxes, these are the errors in the parallax measurements. So here's parallax 0. And here's parallax 1. And there's the errors in the parallaxes. So let's talk about parallax first. So the parallax is 5.5, which means it's quite close. Right? It's interesting. This is an interesting double. So it's quite close. And the parallax errors are quite small. So it's a good, the team considered it a good measurement. It's quite a good measurement of parallax. And you can go and take a look at the rest of this. You'll find probably that the, well, let's look at the RA, sorry, I keep clicking on, if you do that, then you can't see the actual stars. Okay. The proper motion in RA.
Yeah.
For 0, and here's the proper motion in RA for the companion. So you can see that the proper motions are very, very similar.
Yeah.
Right? And the deck proper motions are very similar. So you can see why I would say that this is quite a high likelihood that it's gravitationally balanced. Now, it might actually be in the WDS catalog, and it might have an orbit and everything. So, you know, that's worth looking into. So if it has I haven't put in here whether it has an orbit, but it wouldn't surprise me that this probably has an orbit and everything. Okay. So anyway, that's the whole idea. And I think that's it. That's the whole thing. So you could use this tool to find a bunch of candidate double stars that maybe are in the WDS catalog or maybe aren't. Jocelyn just found 38 that weren't.
Wow.
So they're brand new. He has a September or October paper in the JDSO, and the paper is about finding 38 new double stars with what's he have, a C11, right?
Wow. Wow.
So I'm also interested in the opposite. Am I audible? Can you guys hear me?
Yeah, you're. Yeah.
Am I still soft? I'm sorry about that.
You're good. You're good.
Loud and clear.
Okay, great. So I'm interested in eliminating. Has anyone gone through the WDS and eliminated stars from consideration based on the Gaia data? One team that I had last spring was researching a double star, and at the point of reclassifying it to an optical double based on proper motion and other arguments. And then the Gaia catalog came out, and based on parallax, we learned that the stars were 900 light years apart. And this is a star that had an orbit. And I'm sure there are like bazillions of those that could be eliminated. Has anyone gone through and taken those out?
I certainly haven't, and I don't know, but I imagine the folks in charge of the WDS catalog must be doing those kinds of things now.
Mm-hmm, mm-hmm.
Should ask Brian Mason. Send him an email.
Yeah.
Yeah, maybe. Yeah, that's a good idea. I'll send him an email.
So this is so great. Thank you, Dave. I feel like I could easily teach people and get students now to usefully select double stars to observe. And then I just want to double check with you. So in 2 weeks, I'm going to Houston to the American Association of Physics Teachers conference, and I'm teaching a 4-hour workshop on on this whole program. Is it okay if I share with due credit to you? Can I share this program with people and teach them how to use it?
Yeah, of course. That was kind of the whole idea.
Awesome. Okay.
Yeah, feel free to distribute it as you like to anybody who'd like to put it on their machine.
Okay.
How should the students cite it? Like, for example, if they find, they're probably going to be looking for stars in images to start, and then looking them up in Gaia and in this, using this tool. How should they cite your gravitationally bound index?
I really I haven't come up with a reasonable citation. Just say, so what do you say? Bob,
Private communication.
right. What's the correct way of citing that?
You know what? If I wrote up a quick paper based on this, and then Dave put you as first author and submitted it to the JDSO, then we could have a paper to cite about this.
That's true. We could.
That would be awesome.
Cool.
Also, the acknowledgments.
Yeah, this is going to be amazing. This is going to be so useful. And I had one other question. That was about so in Gaia, when we look up stars on Vizier in Gaia, and we fire up Aladdin, the Aladdin light that's on the Vizier website, it typically says J2000, and maybe we haven't found the option yet for J2015.5, but I wonder if Aladdin also has the 2015.5 thing, just to find how the stars have moved.
Yeah, well, let's see what I put in my notes, because I could have misspoke. It could be that Gaia is J2000 Epic 2015.5.
Oh, okay. What does that mean exactly? So that it made the measurement in 2015.5, but then it's using the proper motion that it found to translate back to where the stars were in 2000. Is that what
Yeah,
that?
so because of the precession of the equinoxes and other smaller factors, there's nutation and there's other issues with starlight, because light has a finite velocity. Actually, the apparent location of the starlight is a little bit different than its actual location, just because the Earth is moving and so forth. So if you make a measurement today, 2018.99 or something, right? 0.9 something, 5 or something, you're actually measuring that, and so your telescope, though, would tell you, or even better, let's say we plate solved that image, and the catalog that we plate solved it against was J2000. So the coordinates in that catalog that we plate solved your image are the coordinates of the world on January 1st, 2000. Which means that since then, the Earth there's been precession of the equinoxes, and there's been other changes in the nutation and so forth. So to get back, but the coordinates that plate solve gave you were the coordinates of the world on J2000, not today. Since that time, so the precession is very well understood, and we can precess things forward and backwards with extraordinarily high precision if you do it correctly. But there's proper motion involved, which can be much less well known. So the proper motion, of course, it wasn't where the star was in 2000. It's where, because of proper motion, has moved since 2000. So I can quote the coordinates in J2000 coordinates, but I have to say that for proper motion reasons, the proper motion, it was recorded, those coordinates were actually recorded today. So if I knew the proper motion, I could translate it back to 2000, or I could leave it alone and just say it's epoch 2018, almost 2019. So you get the idea? So the epoch business is whether or not you've taken proper motion into account and have transformed that too back to 2000 or some other date. So I can say it was J2000 and epoch 2000 or epoch 2000, which means that even though I took the image today, I know the proper motion well enough that I can translate it back to where it would have been.
Gotcha.
On January 1st, 2000.
And those were the coordinates you would give.
Right. So that's why when you state coordinates, you have to give an equinox and an epoch. If you don't, you can be in a little bit of trouble, especially with double stars.
Gotcha.
Okay. Now, I probably misspoke. I think, now that I think about this more clearly, I think Gaia, RA and DEC are J2000.
I was just looking at a draft from April of their paper, and it seemed to be saying a bunch of stuff in 2010.0.
Yeah, that's why we have to be real careful.
Yeah.
So here's what we've got. Symbols on the form. RA and DEC are J2000. Epoch 2015.5.
Yeah.
Okay? So that clears that up.
My simple way of thinking of that is the coordinates would be for 2000, and the separation and position angle would be more appropriate for 2015.
Yep.
Exactly. Just in simple terms.
No, that's really exactly what it means. And a good way of thinking about it.
I have a comment about the index. Since it's more or less the difference in measured properties divided by the uncertainty in those same properties, it seems to me that the signal to noise is a big deal there. And it's going to tend to be smaller for brighter stars, but not too bright, because I think Gaia gets in trouble if things are so bright that they're not really in the design range.
Yeah.
Because it was designed for what? Probably optimized for maybe magnitude 15 to 25.
Exactly. So,
and bright stars nearby especially are just going to be really high signal, maybe some saturation. I don't know if there are safeguards against saturation, but since it's a kind of a trailing device, maybe things are moving so fast that it doesn't saturate unless it's like, I don't know, 6th magnitude or 4th magnitude or something.
as I recall, they designed it for Mag 6 and dimmer, but they were actually able to get useful information to Mag 3. Maybe through image processing techniques or whatever.
Yeah. But in general, I would think that I think the star that you had selected there with a low index was about 9th magnitude.
Yeah.
It's very bright for Gaia and just right for a C11.
Perfect for a C11. Yeah.
So that's kind of a nice optimum. There's plenty of light, probably really good signal noise. They're not so close that their light is messing with each other too much. And maybe that's kind of like the best case. If you go, 5 magnitudes fainter, generally the errors are going to creep up, and probably the index is going to creep up also. But that doesn't mean it's really worse. It just means you're kind of in the range of limitations of the satellite.
Precisely. That's why I want to stress that this isn't telling you that it either is or is not gravitationally bound, but it's only presenting kind of a statistical likelihood that it is, and it's maybe worth a second look. It is really all I'm trying to say.
Yeah.
You're kind of on your own. You can look at this guy and you could say, well, yeah, that's almost for sure that one's gravitationally bound. It has the same proper motion, the same radial velocity, the same parallax, but it could still be accidental without having a lot of accumulated data over the years to show curvature in the relative position of the two stars, so you can actually see the orbit. Then you really can't say even there. I mean, it could be completely accidental.
Yeah.
But it tells you where to look. If you want to go hunting for gravitationally bound doubles that aren't in the WDS catalog, well, here's a tool that kind of it allows you to do that. Then you have to ask yourself, well, is it something that I could then measure with my telescope and with speckle interferometry or whatever other technique you want to use? So let's go hunting for things that aren't a WD, or aren't necessarily a member of the WDS catalog and don't necessarily have 3-band photometry. And let's widen the search range a bit. Suppose, I don't know what this time of year, 18, well, that's summer, but you get the idea. So we'll go to 23. Sky, has become unstable. Zoom is telling me. So this, you may not be able to communicate with me in a couple of minutes. But anyway, let's just do this. Okay, now look at what we've got here. So this one isn't in the WDS catalog, but it's got a really low GB index. The separation is about an arc second. The magnitudes, actually, I could do this with the 700 millimeter telescope at GVL. I could easily do this with a CDK 700 because the magnitude of the secondary is 14.5. So I could actually go and take a look at this and reduce the data using speckle techniques, and I could see for myself if there was a double star there. And it has a low GBI, so it probably has the right stuff to be a candidate. You get the idea.
Yeah, that's great. To do the speckle, you would need a high-speed camera, correct?
We take images. Yes, we have a speckle camera that's taking images, with integration times that are between 10 milliseconds and 100 milliseconds.
Okay, so that's not something we can do with our LCO telescopes that we have access to.
Not unless you have a video camera on it.
No, they don't.
Maybe you could look for nearby doubles that were fairly wide, but also fairly close and had a low GBI. Then you might be able to go after them with a regular CCD image.
Yeah, that's what I would do. I would change the separation criteria in this filter thing in this program.
So
if you took relatively short exposures, you could probably still pick up 2, 3, 4 arc seconds, couldn't you?
We're not really able, I've been working with this recently, not able to get lower than 5. I don't know about you, Calais.
So that's true for us with the Skynet and LCO telescopes, but my student he's hoping to get into speckle and is doing some research on it. He's gotten down to 3 and 4 arcsecond separations using his 10-inch, which is, I don't know how he does it.
Whoa, what kind of camera? Does he have a high-speed camera? Or?
He does, and he thinks he can get into, and I wrote down 10 to 100 milliseconds so that I could ask him if that's in his range. But this is Ryan, you know Ryan Caputo, right, Rachel?
Yeah.
And he was talking about trying speckle and hasn't done it yet, and he's like sort of been learning fire capture a little bit and is very eager to do it, but hasn't done it yet. So I'll mention this to him as a
That's going to be our next training, speckle.
That's another one that I had some instruction from Rick last summer. Thank you so much for that. Like giving him your data cubes to see if he can use those as practice for when he gets his system running.
That was fun.
That was so fun.
There's another area that might be a useful place to look. I don't have any experience with it, but if you look through WDS at some really well-studied stars that have lots of components in the field where people have just, probably taken pretty deep images and found lots of other stars and then observed them. Maybe there's a little bit of motion going on. But some of those are red dwarfs that are way like a minute or 2 minutes away from the primary.
Oh wow!
And yet, if those primary stars are really close by, so that red dwarfs are still visible, which is maybe within 100 light years or so, maybe they are gravitationally bound, and deep CCD images might be a real good place to good use for that.
Cool. I'll mention that.
Especially if they're nearby, they might be really wide. This little old tiny red dwarf hanging out there against a really bright B or A star or something, still big enough to hold on to those little stragglers.
Yeah, we just recently imaged one that was 15th magnitude. It was the D component, I think, in a 4-star system.
Yeah.
Very close to the primary, which was about a magnitude 7. So it was quite a difference, but we were able to get it with a long exposure. That was kind of fun.
Yeah, there might be 10 or 15 magnitudes different.
Yeah. And I'm wondering if it would be useful, or actually I think this might be cool, to compare some of this with, or use the WISE infrared catalog, because there's some techniques there to figure out, I think, actually brown dwarfs, and that might be another whole nother level we could take this.
Yeah.
Wow.
That's a stretch. Maybe you could really get into something there.
Yeah. Huh. So many possibilities. Okay.
Awesome. Well, thank you so much for all of this, all of you, for spending this time. I'm super excited about using this. I'm sure I'll have more questions, but this is a fantastic start. And I'm really excited to start digging into this with students. So thanks so much for building it. And
Yes, all that.
wow.
Great. Well,
Yes, thanks, Dave. It's a really nice one of your many contributions. Thank you.
Yeah.
Very welcome. My pleasure. Another step could be speckle interferometry. So there you have put a high-speed camera, and Rick is an expert at that, and Reed also. So put a high-speed camera on your telescope, and you can actually do some very close levels.
Yeah, that is the next step.
The fun next step.
Very cool. I do want to actually, I am going to write up something about this tool, if that's all right. Probably in relation to me teaching it to I have at least 15 people signed up. They're, paying significant money to take this workshop. And so I'd like to find out what the outcomes of that are going to be. And especially because actually Plane Wave Instruments is funding this little workshop. So if I just wrote up sort of a report with and how we use this, that would be a cool publication, and then it would be something that could be referenced by students in the future.
Wonderful. So let's work together on that.
Awesome. Okay.
Okay?
Oh my gosh. Thank you guys so much. This is amazing.
Okay, super.
Okay, well,
All right.
I need to go do a pickup from dance, but I will be very excited to stay in touch with all of you, and thank you again for spending the time. Have a happy holiday.
Yeah.
Yeah. You too, everyone.
Bye-bye, Kaylee. Thanks for putting this together. Dave, this is a wonderful tool. Thank you very much.
Yeah.
You're very welcome. My pleasure. Let's see what comes out.
Yeah. And Clay, send me the recording, please.
Yes, I will.
Okay, thank you. All right. Bye, everyone.
Bye.
Bye. Take care.